All right. So coming back to this overall idea of internal energy and heat and work. So if we're looking at changes in energy, again, internal changes mean stuff's coming in. Internal energy is calculated as the sum of Q, the heat gained or lost by the system, plus W, the work done by or on the system. And so when the system is doing heat, meaning it's pushing heat out, or when it's doing work and pushing work out, both of those would result in negative energy, decreases in our delta E for the system. When heat comes in, or when the surroundings do work on the system, so the system has work done on it, that is going to increase the internal energy. That's going to bring it up. Now, it is possible to have combinations of those things that are conflicting. Heat gets added to the system, but the system does work. So some energy comes in, some energy goes out. Work's done on the system, but it releases energy. And so we can monitor and track that with this equation and look at the net change. Change in energy is equal to heat plus work. And when it comes to those kinds of calculations, we can get into another concept here of thermochemistry, one that kind of is the entirety of what it is we will be driving for ultimately. And it's something called enthalpy. Enthalpy is our monitor of heat flow in and out of a system. We can define enthalpy as the sum of the internal energy of a system plus the pressure volume product of that system. Now, it is very rare for us to actually measure the enthalpy of a given system, because the actual mark of how much energy a system has at a given moment of time is generally useless to us. What we're usually more concerned with is when that mark changes and monitoring the change. So from now on, when we talk about enthalpy, what we're really going to be talking about is the change in enthalpy. So if you hear me refer to the enthalpy of a reaction or the enthalpy of a system, we're not talking about how much energy that system has at that moment in time. We're talking about how much has its energy changed as we are looking at it. And if we apply that change, the change in enthalpy would be equal to the change in energy plus the change in the pressure volume product. since most chemical reactions occur at a constant pressure, because they're usually conducted in the open atmosphere, we can actually pull this pressure term out of the change, and that will give us this equation here. Change in enthalpy is equal to the change in internal energy plus the pressure times the change in volume. And for reasons that we'll get to in a little bit, if that pressure is held constant, and we are dealing with a specific type of work called pressure volume work, which is associated with gas phase reactions, then enthalpy can be shortened even further, just simply being related to the heat energy. And so again, usually what we are talking about with enthalpy change are changes in heat energy. So looking at the system or looking at the surroundings and making a determination. How much heat is going in that system or coming out of that system? With this definition of enthalpy, we're able to actually finally define a couple of terms that we've been using just kind of loosely for the past year plus. What does it mean to be exothermic? What does it mean to be endothermic? You've heard the terms, you've probably used them. Now we have a context for them. And the context for them is enthalpy. When the change in enthalpy for a system is greater than 0, that is, energy has been brought into the system, heat energy has been brought in. We call that an endothermic process. Endo into thermic heat, heat into the system. When delta H is less than 0, that is negative, it's an exothermic process. Exo meaning out of, thermic heat, heat out of the system. We've been able to tie those things to general observations. If I'm observing a chemical reaction and that reaction feels warm, we've generally said, oh, that's an exothermic reaction. Well, now we have a reason. We have a context for that. The reason it felt warm is because the system was releasing heat, and you, as part of the surroundings feeling that heat, were feeling the release of that heat. So your temperature went up, you were absorbing heat, but you're part of the surroundings. So if the surroundings energy goes up, that must have meant that the system energy went down. Similarly, you do a reaction feels cold. What's going on there? Well, you are part of the surroundings. So when a chemical system or reaction feels cold, that's because it's taking heat from you. You are losing heat. Your system is exothermic, but the chemical system that we're investigating is taking that heat in. So it's endothermic. So let's take a quick check for understanding here. I've got 3 different descriptions of a physical or chemical process. I want you to determine if they are exothermic or endothermic. Okay, so correct answers here. If you were told that you have the wrong answer and it matches what I said, it could have been that you chose the wrong match because it's very specific. It doesn't understand that the words are the same. Okay, if ice melts and turns into liquid water, the ice would have to add energy to do that. It's going to raise its temperature. It's going to require energy to break all the hydrogen bonds and everything else. That would be an endothermic process. We activate hot pack and we put it on an arm. If we're looking at it from the perspective of the hot pad, that'd be an exothermic process. The hot pack is releasing energy. If we take that same hot pack, put it on the arm, we're looking at it from the perspective of the arm is going to feel warmth coming from that. It's because it's absorbing energy. That's an endothermic process. So again, if you got marked wrong, there are 2 endothermics and 2 exothermics. The extra exothermic here was junk. So if you happen to accidentally choose that one as your answer for exothermic, it would have recognized it as a wrong answer, even though the 2 words are exactly the same. So that's one of the reasons why I don't count for correctness for this kind of question, because you just can't. All right. We have a gas confined to a cylinder. When the gas reacts, it absorbs 824 joules of heat from the surroundings and has 0.65 kilojoules of PV work done on it by the surroundings. The questions are, what are delta H and what is delta E? So what we have to remember is that delta H should be equal to the value of Q if we're at a constant pressure. And we're dealing with PV work. Question is, we know it's 824 joules. What is the sign? So we have to think about, okay, which direction is this heat energy going? And we're told it's going into the system. The system is absorbing it. So therefore, it is positive 824 joules. Now for delta E is equal to heat plus work. We've already established that the heat is positive 824 joules. The work is 0.65 kilojoules. We again have to look at this from the perspective of which direction is it going? And once again, we see that the surroundings is doing the work, which means that the energy of that work is coming into the system. This is a positive as well. Now, before we just add these together and call it a day, we've got to understand we've got a unit mismatch here. We've got joules here and kilojoules here. So before I add them together, I've got to get them on the right unit. As I've mentioned before, I feel like it's easier to go from kilojoules to joules by multiplying rather than dividing. So that's what I'm going to do. You could easily go the other way though. 824 joules plus 650 joules give us delta E value of 1474 joules. Which, if we round it properly, because this 0 is not significant, we would need to round to the tens place. So 1470 would be the answer. So when we're doing these heat and work evaluations using delta E, that's the biggest place where we can get tripped up, is failing to recognize when heat is coming in or when energy is coming into the system and when it is leaving the system. All right, any questions about this example? Now, the previous problem made mention of something called PV work. PV work describes a phenomenon that is generally true for most reaction systems in terms of the work that they are capable of doing. If we've got a reaction like most of the ones that we have been working on since the beginning of this class, most of them are incapable of doing work. I add this solution to this solution, we get a precipitate. That precipitate's not doing any work. It's not going to move anything. It's not going to push on anything, create any pressure, change the volume in any kind of way. What we need for this kind of work is gas. Gases give us this kind of work. And when they give us this kind of work, their PV work can be defined as follows. Work is equal to the opposite of P times delta V. Why the negative sign? Because of our sign convention. If work is being done by the system, it is going to push out on the walls of its container and cause them to expand. An expansion of the container would give us a positive delta V. But wait a second, work done by the system should be a negative value. Well, I've got positive delta V pressure can never be negative. How do I get the negative? I've got to add it. That's what that negative sign in the front is. When work is done by the system, delta V is positive. When work is done on the system and the walls are closing in, delta V is negative. And that opposite sign there is going to turn the negative delta V into a positive value to show that work was being done on the system instead of by the system. So here's an example of one way we can get PV work in action. If we have a reaction that produces some sort of gas phase product, that gas phase product would push on the system and cause it to expand. That expansion would be our delta V value. And so in this particular case, we would see that the system is doing work because it caused the container to expand. Yes. So, if you were to drop a soda can that was still sealed onto the floor and suddenly a whole bunch of that carbon dioxide rushed up into the atmosphere of the can would feel harder because the pressure inside was greater, since now those gas bubbles, instead of being dissolved into the soda, are now in the airspace above the soda and are going to push out. And so we're not going to see a delta V in that case. We'll see an increase in pressure though. And so that's a different kind. That's not PV work, but it is a form of work. It would become PV work if the pressure inside became so great that the can ruptured, and then the gases expand as a result. But where it's important for us is if we apply this idea of PV work. Again, here is our definition of enthalpy. Delta H plus delta E, or delta H is equal to delta E plus P delta V. And taking into consideration that E is equal to Q plus W, what we have in this circumstance is our enthalpy change being equal to Q plus W plus P delta V. And if our work is PV work, we can substitute negative P delta V in for W. What I have is negative P delta V plus positive P delta V. So my P delta V terms cancel. That's how I am then able to end up with, if I'm at constant pressure, my delta H, my enthalpy change, is equal to the heat change in those scenarios. So that's where it comes from. Since most of the work that we are dealing with in chemistry is PV work, and since PV work basically is set up as the opposite of that other term in our enthalpy equation, we only need to focus on heat, which makes things way, way easier to do from our perspective. It's a lot easier to focus on heat and know that it has a direct tie to enthalpy than to have to worry about, oh, I got to measure the pressure, I got to measure the volume, did anything change? We can ignore all of that. We can just focus on the heat which in the end is going to come down to a focus on changes in temperature. So just a little example here with PV work. I've got a tank of compressed helium that we're going to inflate 100 balloons with, each at an atmosphere of 1.01 atmospheres. If each balloon is inflated with 4.8 liters of helium, how much PV work is done by the compressed helium? And then we need to express our answer in joules. So our pressure is 1.01 atmospheres, and our volume, we're going to start with no helium in the balloons, to 4.8 liters. So P delta V is going to be 1.01 atmospheres times 4.8 liters. Which is 4.8 liter atmospheres. And this would be per balloon. If I multiply that by the 100 balloons, I end up with 4,800 liter atmospheres as the total work that was done by the system. So if we're looking at it from the perspective of the helium, it would be negative 4,800 liter atmospheres. If we're looking at it from the perspective of the balloon, it'd be positive 4,800. Now, the question was, we have to express our answer in joules. Now, this is not a conversion that you're going to be asked to do very often, but there is a conversion between liter atmospheres and joules. We just need to look it up. And Dr. Google strikes again. 1 liter atmosphere is 101.325 joules. So if I take that 4,800 liter atmospheres times 101.325, we get an insanely large number here. 486,000 joules. Which would be 486 kilojoules. So each balloon had 4.8 liter atmospheres done on it. There were 100 balloons. No, you're right. It is 480. Yep, I multiplied by 1,000. All right, I'll fix that later. Or I'll just change the problem. Okay, so for the original problem, Yes, it would have been 480 liter atmospheres, which would have been 48,600 joules or 48.6 kilojoules. The long and the short of it is when we start getting on that larger scale, you can see why kilojoules become kind of necessary. Any other questions other than pointing out my obvious mistakes? So I'm going to point out a couple of other things here for today, and then we'll kind of pick up the calculations that we need for lab when we get to lab. But one important thing that we do need to understand is that enthalpy is an extensive property. If you remember extensive properties, that means that it does matter based upon how much there is. The more stuff there is, the more prominent that property is going to be. And so in the matter of energy, that means that our energy values that we have here are going to be stoichiometric in some kind of way. So, for example, if I have the conversion, the combustion of hydrogen with oxygen to make water vapor, that reaction is going to release 483.6 kilojoules of energy. Now, that is a stoichiometric amount, meaning in order to get that amount of energy released, I have to have 2 moles of hydrogen gas, 1 mole of oxygen gas, and I have to create 2 moles of water vapor. If I cut those values by half, the energy output would be cut by half as well. If I tripled them, the energy output would be tripled as well. It's a stoichiometric ratio, which means also that if I flip it around and I decide that I'm going to split that water vapor into the hydrogen and the oxygen gas, that energy that was released is now going to be required, is now going to be absorbed. So 483.6 kilojoules of energy was released when it burned. 483.6 kilojoules will be required to split the water back into its elements. Now, this phenomenon of this extensive nature of enthalpy has some really important implications. And a lot of those implications we will get to tomorrow. But I wanted to point out one other thing first. Something we haven't had to consider yet has been the phase of matter. Sure, we've considered phase of matter from the standpoint of, this phase of matter is excluded from the equilibrium and this one is not. But we have to understand now also that the phase of matter associated with our chemical reaction is going to have different energy values associated with it. Gases are going to be higher energy than liquids. Liquids higher energy than solids. And so looking at the difference in our perspective, we've got the same chemical reaction here in both cases. The only difference is that the top one is forming water vapor and the bottom one's forming liquid water. But notice, to form the liquid water, you're not going to get nearly as much energy output. Because some of that extra energy is going to have to go into whatever it takes to condense that vapor and make it a liquid. So different phases of matter are going to give us different energy outputs. So we have to be careful when we start looking at them. And so final problem for today is this one. We've got the reaction of magnesium with oxygen to make magnesium oxide. The enthalpy of that reaction is negative 1204 kilojoules. So just over 1200 kilojoules are released. Since this is a negative value, we know that it is an exothermic reaction. Energy is being released by this process. And if you've ever watched magnesium burn, you know exactly why. That reaction generates lots of heat, lots of light. It's a very energy-giving reaction. Calculate the amount of heat transferred when 3.55 grams of magnesium react. Okay, this one's actually not that bad, because now we're going back to our days of stoichiometry. All we need to do is a conversion, because this balanced chemical equation follows the rules of stoichiometry. Every 2 moles of magnesium will give us 1204 kilojoules of energy. So I can just incorporate that into my unit conversions. 3.55 grams of magnesium. There are 24.31 grams in every mole. And every 2 moles of magnesium will generate 1204 kilojoules. So 3.55 times negative 1204 divided by 24.31 divided by 2. So 3 significant figures is negative 87.9 kilojoules. So that is how much energy is going to be released in this process. All right, any questions here? All right, so get your last participation point for the day. And then before we head over to lab, let me just give you a little bit of context for some of the calculations that you're going to do so that they're not quite as foreign. And that should go a long way to helping you do the analysis when we get there.